Welcome back. This is part 2 of this lesson. We're going to continue immediately from the end of part 1, so let's get started. Now we've talked about the source and destination IP address of these packets, so now let's focus on IP addressing itself. IP addressing is what identifies a device which uses Layer 3 IP networking. Now I'll talk more about how IP addressing is decided upon and assigned in another video. For now I want you to fully understand the structure of an IP address. In this video I'll be focusing on IP version 4 because I have a separate video which will cover IP version 6 in depth. This is an IP address 133.33.3.7. From a pure network connectivity point of view, if you have a valid IP version 4 address, you can send packets to 133.33.3.7 and they will at least start on the journey of getting to this destination. Now there might be blocks in the way, so firewalls or other security restrictions, or the IP could be offline, but packets will move from you over the internet on their way to this IP address. Now this format is known as dotted decimal notation. It's 4 decimal numbers from 0 to 255 separated by dots. So 133.33.3.7. Now all IP addresses are actually formed of 2 different parts. There's the network part, which states which IP network this IP address belongs to, and then the host part, which represents hosts on that network. So in this example, the network is 133.33, and then the hosts on that network can use the remaining part of the IP. In this case, 3.7 is one device on that network, a laptop. A really important part of understanding how your data gets from your location to a remote network is that given 2 IP addresses, how do you tell if they're on the same IP network or different IP networks? If the network part of the IP address matches between 2 different IP addresses, then they're on the same IP network. If not, they're on different IP networks. So you need to be able to calculate for a given IP address which part of that address is the network and which part is for hosts, and by the end of this lesson you will know how to do that. Now IP addresses are not actually dotted decimal. That's how they're represented for humans. They're actually binary numbers. Each decimal part of the IP address is an 8-bit binary number. There are 4 of these per IP version 4 address, and this means that an entire IP address is 32 bits in size, so 4 sets of 8 bits, and each of these 8 bits is known as an octet. You might hear somebody refer to, say, the first and second octet of an IP address, and this is always read left to right. So the first octet in this example is 133, or in binary 100000101, and the second octet is 33, which in binary is 001000001. Now this binary conversion, this is not something which I'm going to cover in this lesson, but I will make sure there's a link attached to the lesson which shows you how to do it. It's just decimal to binary maths, and once you know how it's done, it's really easy to do, even in your head. Now I'm going to talk about how you can determine which IPs are on the same network next, but I wanted to introduce the format of IP addresses first. In this example, this IP address has what's known as a /16 prefix. This means that the first 16 bits represent the network and the rest are for hosts. Now don't worry, I'll talk about how this works in detail coming up next. Because the first 16 bits are network, it means that a second IP address, so 133.33.33.37, because the network part of that matches, so 133.33, then it's on the same IP network. I'm going to detail coming up next how this calculation is done. For now, I want you to be comfortable knowing that if the network component of 2 IP addresses match, then devices are local. If they don't match, then devices are remote. That matters when we start covering IP routing. Now, IP addresses on networks, these are either statically assigned by humans, and this is known as a static IP, or they're assigned automatically by machines, so servers on your network running DHCP server software. Now, DHCP stands for Dynamic Host Configuration Protocol, and this is something I'll be covering in detail in a separate video. On a network, IP addresses need to be unique or bad things happen. Globally, in most cases, IP addresses need to be unique or also bad things happen. So keep that in mind. Generally, when you're dealing with IP addresses, you want them to be unique, especially on your local network. Now let's talk about subnet masks, because these are what helps us determine if IP addresses are local to each other or remote. Subnet masks are a critical part of IP networking. They're configured on Layer 3 interfaces along with IP addresses. What's also configured on most network interfaces is a default gateway. This is an IP address on the local network which packets are forwarded to, generally if the intended destination is not a local IP address. Subnet masks are what allow an IP device to know if an IP address which it's communicating with is on the same network or not, and that influences if the device attempts to communicate directly on the local network or if it needs to use the default gateway. On your home network, for example, your internet router is likely set as your default gateway, so when you browse to netflix.com or interact with AWS, because the IP addresses that you're talking to are not local, then packets from your machine are passed to your router, which is the default gateway. So let's say that we have an IP address 133.33.3.7. Now this alone is just a single address. We don't know which part of it is the network and which part of it is the host component. I just finished talking about how IP addresses are actually binary numbers. This IP address in binary is 100000101, so that's the first octet, and then 001000001, that's the second octet, and then 0000011, that's the third octet, and then finally 0000111, and that's the fourth octet, and that represents 133.33.3.7. So as a reminder, if we're dealing manually with subnet masks, and remember this is something that's generally performed in software by your networking stack, the first thing we need to do is convert the dotted decimal notation into a binary number. Now, along with this IP address, we would generally also configure either statically or using DHCP a subnet mask. In this example, the subnet mask that we have is 255.255.0.0 or /16, and these mean the same thing, and I'll show you why over the next few minutes. A subnet mask represents which part of the IP is for the network. It helps you, or more often a machine, know which part of an IP address is which. To use a subnet mask, you first have to convert it into binary. So 255.255.0.0 is this in binary. We convert it just like an IP address. So the first octet is all ones, the second octet is all ones, the third and fourth octet are all zeros. The /16, which is known as the prefix, this is just shorthand. It's the number of ones in the subnet mask starting from the left. So /16 simply means 16 ones, which is the same as 255.255.0.0 when you convert that into binary. Now, when you have the subnet mask in binary, anything with a 1 represents the network, anything with a 0 represents the host component. So if you overlay a subnet mask and an IP address, both of them in binary, it becomes really easy to tell which part is which. Something else which is really cool is that for a given network, you can calculate the start and end IP addresses of that network. Take, for example, the IP address that's on screen now, so 133.33.3.7. Well, we've converted that into binary, and we've also converted the subnet mask of 255.255.0.0 also into binary, so that's in blue right below the binary IP address. To calculate the start of the network, we begin with the network part of the IP address, and then for the host part we have all zeros. So let's look at what we've done. The subnet mask, where there are ones, this is the network part. So we take the original IP address, and where the subnet mask has ones, that's the network part, so 133.33. Then for the part which is hosts, which is where the subnet mask shows zeros, then we have all zeros. This means that the network starting point is 133.33.0.0. Now to find the end, we take the network component of the IP address again, so where the subnet mask is all ones, that's what we start with, and to work out the end of the network, we take the host component, so where the subnet mask is zeros, and we have all ones in the IP address. So the ending part of this network is 133.33.255.255. So the starting address of a network is the network component of the IP address identified with the subnet mask and then all zeros for the host part of the IP address, and the ending address of the network is the network part of the IP address to start with, and then for the host component we have all ones. So this is how subnet masks work. They're used to identify which part of an IP address is the network part and which is the host part. As long as the network part for two different IP addresses is the same, then we know that both of those IP addresses are on the same IP network. And this is essential so that a machine can identify when it can send data directly on the same local network, or when IP routing needs to be used to transfer packets across different intermediate networks. So it's how your local device, your local laptop, knows to send packets to your internet router for Netflix or AWS, rather than trying to look for both of those systems locally on your local area network. And that's how a router makes that decision too when it's looking where to forward packets to. So using subnet masks and IP addresses, it's how a lot of the intelligence of Layer 3 is used. Now next, I want to spend some time looking at route tables and routes. Let's step through an example of data moving from you to AWS, and I want to keep focus for now on how a router makes a decision where to send data. Packets that you create for AWS will move from your house into your internet provider across the internet, potentially even between countries, and then finally arrive at AWS. Let's step through a simple example. So we start with our house on the left. Next we have our internet provider known as an ISP or Internet Service Provider, and let's call this Meow ISP, and then we have three destination networks. We have AWS, our ISP's upstream provider, and then Netflix. Now we want to communicate with AWS, and so we create a packet on our local device which has our IP address 1.3.3.7 as the source IP address, and it has a destination IP address of 52.217.13.37. Now you're going to have an internet router within your home, and this is where your device will send all of its data through. That router has what's known as a default route, which means all IP traffic is sent to it on its way to Meow ISP. Now I'll explain what a default route is in a second. For now, just assume that all data that you generate within your local network by default is sent through to your internet service provider. So now the packet that you've generated is inside your internet service provider on a router, and this router has multiple network interface cards connecting to all of those remote networks. And let's assume in those remote networks is another router, and each of these routers uses the .1 IP address in each of those networks. So how does the ISP router inside Meow ISP know where to forward your data to? Well, it uses routes and route tables. Every router will have at least one route table. It could have more, which are attached to individual network interfaces. But for now, let's keep things simple and assume that the router within our ISP has a single route table, and it will look something like this. A route table is a collection of routes. Each row in this table is an example route. It will have a destination field and it will have a next hop or a target field. What happens is that every packet which arrives at this router, the router will check the packet's destination. What IP address is this packet destined for? And in this example, it's 52.217.13.37. Now at this point, the router will look for any routes in the route table which match the destination IP address of this packet. If multiple routes match, then it will prefer ones which are more specific. The two routes in yellow, so the top and the bottom, these are examples of fairly specific routes. The one in blue in the middle is the inverse. This is not a specific route. The larger the prefix, so the higher the number after the slash, the more specific the route. So a /32 is the most specific and a /0 is the least specific. A /32 actually represents one single IP address, and a /0, well, this represents all IP addresses. A /24 means that the first 24 bits are for the network and the last 8 bits are for the host. So this matches a network of 256 IP addresses. So for this packet that we have with a destination of 52.217.13.37, we've got two routes which match. The top route, which is 52.217.13.0/24, that network contains the IP address which our packet is destined for, so this matches. But also the middle route, 0.0.0.0/0, this matches because this matches all IP addresses. The middle route is known as a default route. I mentioned before that packets from our home network on the left arrive at our ISP because there's a default route. Well, this 0.0.0.0/0 is an example of a default route. This will match if nothing else does. Because we have two more specific routes in this route table, so the top and bottom, if either of those match, they will be selected rather than the default route in the middle. In this case, the bottom route doesn't match our particular packet, only the top one matches, and so the top route will be selected because it's more specific than the default route. Now for the route that's selected, so the top route, it has a next hop or target field. This is the IP address which the packet is going to be forwarded to get one step closer through to its destination, or in this case to arrive at the actual destination, and so the packet is forwarded through to this address. Routing as a process is where packets are forwarded or routed hop by hop across the internet from source to destination. Route tables are the thing which enables this. Route tables can be statically populated, or there are protocols such as BGP or the Border Gateway Protocol which allow routers to communicate with each other to exchange which networks they know about, and this is how the core of the internet functions. One important thing that you need to understand though is that when our ISP router is forwarding the packet through to the AWS router, it's forwarding it at layer 2. It wraps the packet in a frame. The packet doesn't change. The frame though, it has the AWS router's MAC address as its destination. That's how the packet gets to the AWS router. But how do we determine the MAC address of the AWS router in this example? For that, we use something called the Address Resolution Protocol, and that's what I'm going to be covering next. This is the end of part 2 of this lesson. It's a pretty complex lesson, and so I wanted to give you the opportunity to take a small break, maybe stretch your legs, or make another coffee. Part 3 will continue immediately from this point, so go ahead, complete this video, and when you're ready, I look forward to you joining me in part 3.